Okay, welcome. In this video we're going to take a look at creating an automatic joint system or procedural joint system. This is really easy. We're just going to go ahead and we're going to turn these two boxes into particles, and we're going to have them do a p-search at birth, look around for other box particles, and create a joint in between them just using an averaged world position. This isn't really the best way to create joints, but it is the easiest. The reason it's not the best is because if you have some kind of funky shaped particles, that averaged world position between the two particles, might be inside the mesh or something. So we'll take a look at, in the next video, we'll take a look at using an intersect method for doing an intersect in between the two particles and figuring out where that joint should be. But for this case, we can go ahead and be pretty simple. And actually, we're going to go ahead and just start off. Joints are all based on this shape collision, at least the SC joints. If you use or want to use PhysX as your collision engine, you can certainly do that. Unfortunately, you will have to end up using the actual joint helper objects, and this is the PhysX joint helper object out here. And so you probably want to come up with some kind of script that does a little voxel array calculation between objects and creates those PhysX joint helpers ahead of time. Unfortunately, there are no PhysX built-in operators, kind of like we have for SC. SC has this whole category of operators. It's got the actual SC collision engine itself, and then we have, of course, SC joint for creating joints. Then we have SC joint counter, which we can actually either use one or two particles, and we can count the number of joints being affected by that particle. And then lastly, of course, we have joint data, which we can use. We use a joint input, and then we can either, let's say visible inputs, we can either set joint information by using the inputs, or we can actually query it and get to the outputs and use that data for something else. Okay, but in our case we're going to be focusing strictly on the SC joints, and because we can create those procedurally. So we're going to go ahead and remove that, and we do need an SC, and we're going to need some gravity and collision, so we're just going to go ahead and use a black box called SC basic. It just creates that basic SC system. We're going to pick our collision environment object, it's that sphere, set that collision environment and hide it, and then we're going to go ahead and also pick our two boxes to be the objects particles, and hide those as well. Let's go ahead and manage our groups a little bit here. Let's set them all to none and display mesh, and then we'll also go ahead and turn their voxel grid to 1. And what that does is that gives us kind of an optimized, face-accurate kind of collision mode. Okay, so we've got those two objects. We've got gravity. We've got an SC operator in here. So of course these objects fall down, and there's no joints in between them, so they just fall like they would if they were separate objects. And so let's go ahead and create our joint in between the two of them. Call this auto joint 1. And so for auto joint 1, all we really need to do is have the objects, and that might be kind of a bad name for a particle group, but the objects at birth, we want them to do a p-search. Let's get that p-search, and we're going to control when that p-search happens, because p-search is a pretty CPU expensive function. So we're going to control that specifically only at one time. We're going to use that particle age to control when that happens. Particle who is going to be doing the searching is our objects, and the particle group that it's searching for are other objects. So we'll connect that into the group input. And let's use our handy dandy line tool to get an idea of what kind of distances we need to search for. So 50, 60 units should be fine. Let's do 50. Okay, so objects at birth, going to search around the particles they find. We'll go ahead and just create a joint between them. So we'll drop an SC joint out here. We're going to create a joint from the particle who's doing the searching to all of the found PIDs that it can find. So if there's a whole bunch of different particles around, it's going to go ahead and create a joint every time. So just remember that the psearch functionality is it's iterative when on these outputs. So if it finds multiple PIDs, it's going to go ahead and update this for every pair, for each of the for the particle who's doing the searching, with every found PID that it finds. And of course, all these SC operators, SC joint data, SC joint counter, all of them, you have to set the collision field here, this drop down, to specify which SC operator to use, which is this one. Okay, so we'll set that to be SC. Let's use a fixed joint type for the moment. And you can see our objects just kind of jumped there. And that is because we have not specified the positions yet. The positions are a little bit funky. The position from and to are exposed by default. There's also the world position. Position from and to, it might sound really intuitive, like, hey, I want to connect from this particle's position to the other particle's position, but it's a little strange and a little different, because joints in TP are actually, they occupy a single point in space. So you would have to take this particle's position, figure out its position, and then that offset to that middle point where the joint's going to be. And then also in reverse, you have to do that for the position too. So that gets pretty complicated. I mean, if you try to just stick these two positions here and connect those, you'll see that these two will kind of get smushed up together. And well, in that case, they didn't. That was nice. Maybe it's the fixed joint type. But typically, we tend to avoid the position from, position to. You can end up seeing some rather weird behavior sometimes. So what we usually do is a vector averaging. So we'll use VOPs, and then we'll take vector 1 plus vector 2, using them as positions, divide them by 2 to get the average position. And remember, if you just take the particle output here and connect that to this expression operator's vector input, it's going to go ahead and pull the position information in. So we'll grab that, and then that average position, we'll set that as the world position for the joint. And so that just specifies the actual one position for that joint. Really prefer the world position over the position from, position to. Having to do that extra calculating, it's just more work than it needs to be. Okay, so we've got some joints going on there. So this is going to be pretty interesting. We actually kind of want to see these joints, because what's happening right now is, and of course the way TP works, when we specify this PPassAB, or the group reference here for objects, first it starts with the first object particle at birth. It does its searching for other objects, and then it creates a joint for it. And then for the next object's particle, it's going to do at birth, it's going to search around for other objects, particles, and create a joint. So what's happening is this particle here is actually searching, finding this one, creates a joint, and then this particle here searches, finds this guy, creates a joint. So there's actually two joints being created. And that's usually not a problem, and in fact sometimes it can be really creative if you want to start mixing joint types. If you want to mix maybe wobble with spherical, or wobble and ball, all kinds of combinations there. But in our case, we generally tend to only want one joint in between a specific pair of particles. We are going to end up in a case here in a minute where we're going to create a whole bunch more of these boxes and have a whole bunch of auto jointing going on. But for now, we just want to go ahead and just start with a simple 2 particles. But let's actually do a little kind of debug, and we want to actually see where those joints are being created. So we're going to use it SC joint data to create, or actually access, some of this joint information. And well, we don't really need to. We could just say position born. Let's create a new particle group here. We'll call this joint marker. Display those as PIDs. We'll make them kind of a purplish pink color. And then we could just take that average vector position So disable that for the moment. And we want to create those in the joint marker. We want one per call. So for each joint that's created, lifespan, we'll just set that to 1, no speed, no alignment difference. And so what you can see is that we have kind of this garbled, mixed up text there, showing that there's actually 2 PIDs overlapping, because we have, of course, 2 joints being created. So let's go ahead and look at a really easy way to limit how many joints are being created. Probably the first and simplest way is using just a simple expression for greater than or less than, because what we want to do is look at the PIDs for these objects. And so we've got PID 1, PID 2, and we can just test and say, hey, if I'm PID 1, or if my PID is less than the found PID, then go ahead and create the joint. And so what's going to happen is particle 1 compares to particle 2, and of course 1 is less than 2, so it creates the joint. And then when particle 2 starts doing the searching, then it finds particle 1, but 2 is not less than 1, so it cannot create the joint. So we'll go ahead and just drop this in here and see it. Less than. So we want to grab our particle, and we're going to feed that into a scalar. It's going to use that as the PID, and then we're going to go ahead and take the found PIDs and use this. We'll go ahead and just control the on for this SC joint. So when these joints are created, will be controlled by this less than. So if the particle ID A is less than B, then it's going to evaluate true as 1, otherwise false. We'll take that and use that into the SC joint. And now, let's see what we have here. Well, we still see garbled text, so something must be going on there. Well, this is kind of an interesting thing. We still see garbled text because our position born has no limiter to when it actually happens. So it still just takes that particle 2 and particle 1, averages their position, and then creates that. So we actually have to use that less than to also check the joint marker. So now watch, we'll just get 1. Okay, so now we get just a very clear number 3 there. Another way that we can set this up so that we can just not have to control that on is by using our SC joint data. We'll expose the world position and feed that right into here. Okay, so 2 particles creates a joint in between them. We're showing that joint as a joint marker. Normally joints, exist just kind of as a piece of data, a single position in space, and then it is based on the I forget if it's the face coordinates of the object, or it's definitely an object space for each particle. But we can go ahead and look at it in world space. Okay, so we've got some particles going. Let's go ahead and create a whole bunch more of them. And we'll actually be a little procedural here, and instead of just pulling in these 2 objects, we're going to go ahead and use a birth. Well, maybe, you know what, maybe we'll do it a little bit different. Let's try this. Okay, so we've got a source plane that we can work with, and we're going to go ahead and use that as a node. And then we'll get that surface position. Node. Make sure we pick our node. That's always a big problem. And then we're going to go ahead and use a couple iterators to control some UV coordinates. We'll go ahead and feed this into the, this will be our X value, this will be our Y value. And we'll go ahead and feed this into the UVW, and then that UVW will then come out here, and we will use a position born. So this is where we'll create our objects. We'll do one per call, lifespan nice and long, no speed, no alignment change. Okay, so let's go ahead and create some iterations here. So actually what we'll do is we'll set up these iterators to actually use the same count value. So we'll just use an integer. And for now we'll set it to 10. Grab that there and there. Oh, but you know what? UV space is going to be in 0 to 1, so let's use number normalize. Okay, let's see what we have. So, wow, too many. Let's, oh, you know what? It's automatically creating the joints in between them too. So let's turn off the joint rule. Let's actually go ahead and give these new object particles some shape so we can deal with those. Oops. Okay, no size variation. Let's go ahead and make them like that. And then let's go ahead and add a scale operator there. And we'll go ahead and flatten them out. Okay, so we've got a whole bunch of objects now. Let's actually reduce that a little bit. And we'll make them a little bit bigger to fill that gap. Okay, so when we have a whole bunch of objects, particles, these orange guys, we'll go ahead and turn on the auto jointing. And you can see now we get all these PIDs being created in here. And so that's kind of helpful. That shows us all the positions where joints are being created. And we're still doing that check, so it's only the less than. So if this PID is less than this PID, then it's able to create that joint. But for particle IDs who are larger than the particles that they find, they don't create that joint. So that's just I'm not sure if we even did the other way that you can actually limit these. Controlling when this happens is pretty important. So let's look at another method you can use. You can actually pull out a joint counter, and you can count the number of joints between these two particles. We can count both of the joints either from or to the particles. Let's just jump in here. It's kind of interesting, much like get reference, if we have particle A and particle B here, joints have a directional kind of interpretation to them. It's from one particle to another particle. So there's definitely not quite a hierarchy, but a directional characteristic about them. Okay, so if we're going to count these joints, we obviously need again to specify which SC we're using. We're going to count the total number of joints. And remember, we're just looking at an alternative method to limit these joints. And then we can actually get this number of joints, test it with a threshold, and if it's low enough that we can control this SC joint turning on. So come up here, threshold. Let's get that number of joints. So here's where you have to be really careful and think about what you're doing, if not everywhere else. But you have to think, okay, how many joints should these two already have? And in our case, we only want them to have 0. So there should be 0 joints in between them. And if there are 0, oops, yeah, and we'll see a little, that looked like a little timing problem there. We'll check that in a second. Okay, well, we had a problem with our iterators. They were continuing to fire, and so we would get more and more joints being created. You can see that we've got these lots of these objects particles starting to overlap. So we have to limit I have to limit when these iterators are turning on. So use just a time interval for that. This is actually a pretty good little black box. Let's go ahead and we'll cut this. Create a new dynamic set called birth iterate UVW. Okay, so here's our particles. Sorry, this is kind of the big detour. We want to limit the number of joints in between those two particles. In this case, we can use a joint counter and just look at the number of joints currently occurring between those two particles, and if that number is within whatever threshold we want, then we can go ahead and then turn on that joint. Be careful if you set this to like 0 and 1, because what this will mean is, hey, between this specific object particle that we're currently looking at, it found some other particle. There is already one joint in between them, and so, well, there's still one joint that's still valid with this setting, and so we can go ahead and also create a second joint. So just be careful that you control the number of joints in between your particles very, very carefully. Okay, so there are all of the joints in between these guys, these particles, and we're going to go ahead and look at our joint. It's set to fixed, so we'll go ahead and just let it play, and it does its little bounce there. Now you do see a little problem, of course. You see these penetrations occurring where these objects are going through the collision environment. It's probably because our sampling is set to per frame. Per frame is really not accurate enough in most cases, and in fact, just on quite a few productions, the samples per second for joint stability, joints become more stable the more samples there are per second. So if we were in film frame rate here, and we set this to 48 is per half frame. Per half frame, 48 samples a second. The joints will be, they'll be pretty stable in a lot of cases. But if you really want good stable joints, it's highly suggest 4 samples per frame, or in our case, at film time, that's going to be 96 samples a second. Just because what will happen is the smaller amount of time samples, it allows the joints to calculate with less error and less movement in them, I guess. And so you would see cases at per frame where a joint is trying to correct itself, especially if it's not breakable, and then it will just kind of generate so much energy it'll just kind of fly out and everything explodes. So that's kind of a big problem. If you see if you see your sims exploding, check your joint to see if it's actually breakable or not, and then also check your samples, and definitely go for 4 samples a frame or more. Okay, so let's do a little playing around here. Let's set these actually to spherical, and we'll leave breakable off for the moment, and then we'll just go ahead and drop it so we can see how that all kind of shakes around. And we get kind of an interesting pattern in there. If you look at where these joints are located, it's basically looks like almost a definite grid there in between each of them and diagonally. So this is quite a few joints that's going to kind of limit and constrict that motion. If we do, maybe let's go into the P-search and start lowering this. We can see that we can kind of change that joint pattern and reduce the number of overall joints that we're going to have. So this will be a little bit interesting. It looks like some of these joints are not being created along these sides. Yeah, exactly. So it's basically just along these whole strands. So we're going to want a little bit more in there. Okay. Okay, so as you can see, it's pretty simple to set up the automatic jointing. You just kind of have to determine when you want to create that SC joint. Doing a p-search at birth is a pretty good way. There's also the other way that I think we'll take a look at in the next sample file, where when an object, there's the classic example of the rolling boulder falling down and colliding with something, and you can use that actual collision time. You can just take the collision particle A, collision particle B. Of course, we're going to specify the SC. Then we can actually create a joint between those two particles when they collide. We'll take a look at that here in the next video, and then after that we'll go on and look at setting up an intersect system so that we can actually do surface accurate jointing instead of just average positions. So we'll go ahead and save this out as SC4 auto joint system 1, and this will be the ending file, and then we'll go ahead and move on.